Today, I'm going to try to explain to you global winds. Global winds can be a pretty hard topic for students to understand. It can be a hard topic for adults to understand. There's a lot of variables in here. You're going to have to excuse me if I mess up a little bit as I try to go through this lesson. First thing you can see here is I have my sun over here, my earth over here. I put my earth in my equinox axial tilt just to make it easier for you to understand what's going on here. That obviously means I don't have it tilted away, which would be winter in the northern hemisphere, or tilted towards, which would be summer in the northern hemisphere. You can see I've drawn a few lines of latitude, the equator, our tropical lines, and our two circles for the Arctic and the Antarctic. First off, as we know, the sun warms our planet through the process of radiation. But because of the curvature of our planet, it heats it unevenly. And this is due to the fact that in this region here, the sun rays are more direct and more focused because they come in at a 90-degree angle. Up here, it's much, much steeper angle, or what we call indirect, which causes the same amount of sunlight to be spread over a larger area. So these two regions here do not get heated as effectively as this region. Because this region is hotter, that heat through conduction is transferred to the air above it, and that air takes on some of the properties of this region. Because this region here, again being warmer, the air right along the equator in this area is always being warmed more effectively, causing it to rise. And this makes what we call an area of low pressure. I'll put the universal symbol for low pressure, which is a capital L. Now, up here and down here, because our air takes on the characteristics of the land or water mass below it, this air is not rising because it's not getting hotter. It's contracting. It's becoming more dense compared to the air down here. The air down here being less dense, rising because it's getting heated better. This air down here is up here and down here is contracting because it's getting colder, making it more dense. More dense means there's more air. It's going to make areas of high pressure here and here. Now, as we've talked many times earlier, high pressure, more air, low pressure, less air. High tries to move to low to do balance. So these two high pressures globally are always trying to make it here. Okay? So as they try to do that, though, something happens. These highs are trying to head south here and north here. As this tries to move this way and this tries to move that way, something happens. The air, as it's going against the ground through the process of friction, starts to warm up. And as it warms up, it gets less dense. And it starts to rise, which creates here, and this is usually around 60 degrees north and 60 degrees south, it starts to warm and rise again because of it's picking up heat from the ground and also due to friction as it's moving along the surface. So unfortunately for it, this air never makes it to the equator. It's trying to, but it heats up and it then actually becomes an area of low pressure as it rises. So then we get another area of low pressure. Something similar happens here. This air here is rising. Okay, as it moves away from its heat source, though, it starts to cool. Usually, because it's along the tropics too, this area is pulling up a lot of moisture with it through the process of evaporation. And as it cools, as it goes up, all that water then usually forms rain, and that rain then comes down. That's one of the reasons why the tropics get so much rain, because the heat crosses low pressure, which pulls moisture in the atmosphere, which then cools as it moves away from the heat source, the conduction with the earth, and then all that water then comes right back down. Anybody's ever visited Florida, you understand this. You know that it usually rains about once a day, and it's pretty hard, and then it's sunny again. Anyway, so this air, as it rises, it also cools because it's moving away from its heat source. And it gets cold enough to the point where it hits what we call the tropopause, the layer between the troposphere, the weather sphere where we live, and the stratosphere, where the ozone's being causing that layer to be warmed as it takes in some of the nastiest UV light from the sun. So the air, as it rises, it hits a pocket. Remember, this is rising because it's less dense. It hits a layer where the air above it's less dense because it's also being warmed from incoming solar radiation being absorbed by the ozone. So this air then cools, and it kind of just splatters in two different directions, dropping its moisture back down. And then eventually it sinks. And because it lost a lot of its moisture as it rose and cooled, this becomes pretty cold, dry air. And it starts to sink. So about 30 degrees north and south, we get another high pressure area where this stuff sinks down towards the earth, and it's very, very dry air because it's lost a lot of its moisture as it rose up. That is why many of our major deserts are at 30 degrees north and 30 degrees south of the equator. As the air comes down, okay, it then hits the earth, and now it's an area of high pressure. And this local area of high pressure then tries to move towards lows. And we've already established two lows, one here, one here. So this air moves this way. Of course, through conduction and friction, it also then starts to warm. And you can start to see the formation of a convection cell. Now this convection cell runs the entire belts around the planet. Okay, but there she is, rising and cooling between 0 degrees, the equator, and about 30 degrees north and south, above the tropics slightly. We get two global belts of air moving, in this case this way, and in this case this way, towards the equator, along the surface. You need to make sure you understand that, along the surface. It's moving along the surface, this way and that way. Up here, it's moving the opposite direction. So let's go back to the polar regions. I just want to finish those off. This air, of course, rises, moves away from its heat source, and then it sinks, moves away from its heat source, and it also then sinks back down. Okay. Like I said, desert regions here and here, technically, our poles are desert regions. They don't receive a lot of rainfall. Just what they receive doesn't, evaporate. So that's why we get a buildup in our large ice masses here and here. So we can see we have two convection cells here and here, and then two more here and here. Well, what about the middle latitudes between 30 and 60 degrees? Well, we can see the motions already built for this as to what happens. As this cold descending air hits here, it moves in two different directions. It just hits the earth and splatters in both directions. So now we have this high, which is going to move towards this low here. But of course, as it moves towards it, through frictional forces, it's going to pick up heat and reinforce that low. So that's going to rise up. Again, it's going to hit our tropopause, which is going to cause this to splatter and then move back this way. Same thing happens in the south, where the air will try to move towards from the high to the low, but as it does it, it's going to heat up. And it's going to rise around 60. Again, this is 60 here, 60 here. Because you have this rising air, these are also going to be areas of heavy rain in terms of rainfall. Again, dry, drier, dry, dry. So really it is the part of the global wind patterns do actually determine where areas get rain and what areas don't. Again, as this rises up, it's going to cool. It's going to complete the pattern. And what you're going to see here, probably poorly drawn by me, I apologize, is you're going to get 1, 2, 3, 4, 5, 6 global convection cells, which are going to cause what we call global winds, and that's the wind that occurs along the surface where we are. Okay, and you're going to also get an opposite pattern, completing convection cell, up higher in the atmosphere. So if wind's flowing this way on the surface, it's flowing that way, opposite direction, along the top of the troposphere. So just looking at this, that means our wind patterns, our global patterns, should, in terms of what we see, look kind of like this, where wind is going this way. Along the equator, all the wind's trying to move to the equator. Here, our wind is trying to move this way. I'm just following these arrows here. In our middle latitudes, again, just following the arrows. And then up here, it's trying to move south. Again, just following the arrows. And that's the pattern we should see. However, there is one variable we forgot, and that is that below this atmosphere, below this wind, the Earth is rotating. And because the Earth is rotating, these wind patterns do not appear to move to a straight line to us, because the Earth rotates underneath them, which causes the winds to bend. So even though we have these established patterns, another variable, rotation of the Earth, this is known as the Coriolis Effect, actually causes these winds to bend in a certain direction. Now our Earth is going to be rotating counterclockwise. That means it's going to be rotating this way underneath these winds. So I'm going to take all my winds out. Bye-bye winds. And draw in what they should look like due to the Coriolis effect, the rotation of the Earth. So these winds are trying to move to the equator, but the Earth is rotating underneath it. So what that causes, is because the Earth's rotating underneath it, it causes these winds to bend like this due to the Earth rotating underneath it. And we call these winds the trade winds. Historically, as people tried to come from Europe to the New World, they wanted to catch these winds when they were using sails instead of our engine-powered boats of today. So these would pull you or move you towards, of course, the New World. The only problem is if you get in here, you can get stuck because the wind isn't moving sideways, it's moving up. Now, the wind here, from 30 to 60, it's trying to go north. Problem is, the Earth rotates underneath it, so it gets deflected this way. We call these our prevailing westerlies, because they come from the west. So the wind goes from what we call here, this would be southwest, towards the northeast. And then for our final wind pattern, this wind's trying to move south from the poles, but because of the rotation of the Earth, it bends towards the east. And we get our polar easterlies. So these are our global wind patterns that we get. What do they mean in terms of Pennsylvania? Pennsylvania, where we live, we're about 40 degrees. I'm going to put a dot here. What this means in terms of Pennsylvania for our weather patterns globally, our weather comes from the west. It comes more specifically from the southwest, because the prevailing westerlies move air masses from the southwest towards us in Pennsylvania. So that's why in class your teacher's probably always telling you, if you want to know what the weather's like, in all likelihood, look to what's happening slightly to our southwest, and that'll tell you what our weather will be. This is global wind patterns. I hope this helps you understand it. It is a pretty complicated topic in the end for people to understand. Lots of different things here going on. We have differential heating causing different highs and lows. We have convection cells. Then we bring in, again, rotation of the Earth, causing a bending of these patterns. And we also even have climate zones caused because of this, where we have areas that are always very warm and receiving lots of rainfall, areas that are always dry because the wind is descending, or the air is descending here and here, causing those to be almost usually sometimes like desert-like conditions. In terms of history, we also have things like people riding these winds this way. And then on the return trips, I didn't mention, they would try to get up in here and ride these. Places they would try to avoid or get out of quickly was wherever, and this is when sails were used for transportation across our oceans. You really would want to avoid areas where air is coming down or rising, because the wind, as you can see here, is moving up or moving down, and not the sideways directions that the boats would need for their sails. There is a lot more that will be shared in this PowerPoint or this Nearpod, but I hope this helps you understand global winds.